everyone. So my name is Łukasz Kaczmarczyk, and we will show you some in fast way how you can solve the PDEs using MoFEM, and I will focus on the design and sustainable code development. So I will start with the school program for this part. I will give an introduction about code design, heterogeneous and hierarchical basis, what are the pipelines, the general idea of them, and why we're using them. Honk will tell you about user data operators and simple interface. And we will present you how you can use that ideas to solve Poisson problem. Then we'll look at the linear acoustics and how to approximate complex variables, forms integrators. And finally, Carol will tell about the elasticity and how you can implement the code which works simultaneously both in 2D and 3D case, and how you can then the same code easily without the effort expand to the large strings, so that you don't waste the effort of implementing 3 codes at once. You have one code which works and you can test it quickly. And last talk will be from Andre, and he will tell you about the mixed formulation, HDIF and H-car spaces, error estimation, and the p-adaptivity. So and we will have a summary at the end. Before I will try to convince you to MoFEM and the ways how we do the things, I want to encourage you to look not necessarily into the MoFEM, into contribute to the open finite element community. And there is many other codes than MoFEM which are on the market, and why you should join one of them, not necessarily us. So first thing is that for most cases, when you look, the code is written by PhD students. Sometimes it's written by postdocs, less often by professors, but the professors really know how to write the code. So typically, research software is written by inexperienced people which learn how to do that. But once they know, they have no time to do it. So, and no many research codes live because of that beyond the PhD, because when people will move to some other place, development is discontinued. And in few years' time, we don't know how to run it. So such code is not sustainable. We have a problem with the track record of the code itself. We write the papers, but the code has no track record, and there is no pathway how you can use that code in the industry. And industry, that's why, is bound to use the commercial codes, not the research codes. So you have to break somehow that barrier. And finite element code is complex. And in fact, if you want to do it really well, it takes many PhDs, in the sense that it takes many years, longer span of time than the single PhD. You're doing that for decades. In fact, if you look at the serious codes, they are developed for 20, 30 years and more. So successful open research code are developed by the community, so that the programming is not isolated work. It's a big social aspect of it. And you have to engage the community, and then you're building a very complex structure if many people contributing with the various sets of the skills. So that's what is offered to you by when you join some finite element community, not develop it in isolation or small group. So we created MoFEM initially in the Glasgow Computational Engineering Center. And you can go to the MoFEM webpage, MoFEM GLA AC UK, to see how it looks like. You will find out there are tutorials. Some of those tutorials which are on the webpage in the development section will be described later on. You can read about MoFEM in the JOS journal, and MoFEM is supplemented by a set of the different toolkits, or we call it then user modules, that they are developed separately for industrial or PhD needs, and they are not part of the MoFEM, and they have a different licensing depending on the needs. So then we have, for example, acoustic code. You have a submarine here, and topological optimization, bone remodeling, shells and plates, fracture mechanics, contact, and much more. So what is the code in the nutshell? So first of all, is the core library has 250,000 of lines, but it's developed by 20 contributors, maybe more. In fact, it's difficult to track, and it's developed for 8 years. So we are relatively young code. So it's time to join us and then build things together. If you will think about that code with the tests and the validation which we have to do it, for a single programmer working 5 days in the week, professional for programming, it will take us 64 years to do it. So this is large volume of the knowledge accumulated in it. It's mostly written in C++. I know that is a steep learning line, but you have a benefits from using C++. At the end, you have a speed and you have a great flexibility to do the things in the novel and the different way. It has 70 tutorials, and we are writing more. And we have tests which are run on Jenkins and submitted to CDASH. This is automatized process. License is GNU license to protect all developers. So what that means that no one will take your code and use it for own benefit. You have to agree for that, and GNU license protects you. So you can freely contribute without the worrying that someone will use your work without your permission. It works on Linux, Mac OS. When you have when you install Docker, you can run it in Linux, but as well you can run it as a cloud computing. So you can run it in the Jupyter Hub, Jupyter Notebooks. This is how we give it to the bigger public. What it offers? It offers heterogeneous and hierarchical arbitrary order approximation basis. I will explain later on what that means. It supports wide ranges of spaces from L2, H1, HCal, HDiff, so you can solve the solid mechanics problem, fluid mechanics, and electromagnetics if you like. So for example, this is around 300 lines of the code in MoFEM that you have a distributed mesh. It's coarse because we have high order approximation basis. You can solve the electromagnetic problem with the coil in the middle. And then at the end, you can run the particles in the cell when the charged particles are driven by the Lorentz force. Andrei will talk more about the HCal spaces, but you can see as well the tutorials max 1 and max 0 and max 1 for this problem, which you can see over here. Code support heterogeneous meshes, so we can mix triangles with quads, prism with the tetrahedrons. You have a great flexibility. There are data structures which handles different things. They handles multiple fields for coupled or mixed problems, multiple subdomains. You can mix formulations. You can do mixed formulations. You can integrate of the skeleton. Data structures handles that. Easy to parallelize. Every test which we show can be run on the parallel computer on the distributed memory. And code reading various formats from MET format used by Salome, our ADF, our industrial partner, Gmesh, Qubit, and so on. The key thing is that we take a big effort that you can easily transform the information about the boundary conditions from the mesh into the code. And much more, but we have no time to discuss that. What are the MoFEM origins? So we develop it to deal with the gas cool reactors, to model fracture of the gas cool reactors. And we do that because the commercial codes fail to do that. So somehow there is a big incentive to industry to search for alternative solutions. And MoFEM was selected from many codes in 2017 finally, and now is used in the practice by engineers in the EDF and Jacobs to solve the practical problems. They even write the whole interface around it, they call it graphite workbench. IGR reactors contribute around 15% to the energy production in the UK, and they are located, as you can see on that map. We are so successful that by creating a software, we created the impact case for REF 2021. So this is our recent achievement. It's, as I said, so in order to compete with the industry, we have to propose novel finite element technology. And a code is free and open. It's a research code, but we try to develop that code professionally. Okay, wait a second. So this problem about the fracture, why it's so complex? Because it's a multi-physics. We're dealing with radiation, deterioration of the material due to oxidation. We have more than 10 different approximation fields on problems like that, which approximate various things. We have a complex boundary conditions, contacts, spring elements through which crack has to propagate. We have a heterogeneous approximation spaces that in order to get the efficiency, we have to raise the approximation order near the crack tip. It's running in the parallel. It's topology evolving in the continuous way. And the biggest challenge, in fact, is that you're working in academia. What that mean? That the people are coming and going. This is not like in industrial development of code that you have a set of the same people which working together for a long time. There are postdocs which finish their postdoc and they going somewhere else. They getting a lectureship position. So then you develop the code over in time and space. So your code itself has to be designed in such a way that allow to accumulate knowledge and transfer the knowledge from one generation to another. And it has to satisfy at the end standards of the nuclear industry. Okay, so what is the special thing about the MoFEM design? It's that we appreciate the fact that the real life industrial problems are complex, like a space shuttle. So we have to find a way how we can take any complex problem and decompose that into many simple tasks. And each part can be tested independently. It can be tested by various people, PhD student, written by the PhD student, postdoc, or whatever, human resources professor, and then when you have that, you have to find code have to allow you to divide the work into the groups, and then it has to allow you to put everything back efficiently, that everything works at the end. So what is the special? So then we divide we created the special tools in MoFEM, like pipelines, which I will focus on that, but there are other things which allow you to do that thing. Develop the research code for industry with the complexities of the working in the academia. So every finite element program, what every finite element program needs, it needs something which reading the meshes, something which create the approximation basis on the finite elements. Finite elements itself with the operators, differential operators on them, integration rules, linear algebra, and the solvers, linear, time solver, nonlinear solvers, eigensolvers, and some optimization tools sometimes, depending what you want to do. So, of course, we don't develop everything from scratch. We have this, we have this software ecosystem. And this software ecosystem is based on 3 legs for stability. First thing is MOAP, is which this is library, which manage the topology, and through that library we can read the various formats, and then you can do very complex operation on the mesh and manage data on the mesh itself, block sets, side sets to manage boundary conditions. We have a PETC which manage algebra for us on the distributed processors and the solvers, and in the middle of that is a MoFEM, which transfer the information from topology into the system of the algebraic equations, which you potentially solve in the sequential way. There are other things like mfront. This is the library which is set of the different material models. ftensor, which allow us to do a very fast calculations with the tensors from second, third, fourth order tensors, explore the symmetry of those tensors. We modified that library for the needs of the MoFEM, and everything is managed. This complex ecosystem is installed by SPAC. This is packaging managing system, which take care about how to install that in the simplest possible way. What is the structure? So typically you start with the physical model. We working with the ROM in the continuum mechanics. Then when we have a mechanical model, because it's continuum mechanics, is lead to the partial differential equations, system of the partial differential equations. So we have a mathematical model. Typically, those equations we cannot solve. There is no analytical solution because there are non-linearities and other features. So then we use the discretization techniques, numerical methods for do that. And then again, there are three blocks in the core library. We have a core library which has those three blocks, three legs: MOAP, MoFEM, and PETC. And user just using the interface, wrapped interface to read the mesh, add the fields as many, set up the program, create the finite element, implement user data operator. You will see what that is later on. Solve the problem and post-process results. And this is user module. It could be a separate repository. So I will explain what this is Coriolis law, and then imagine that you have a solid shell element and you can estimate a posteriori error. So when you solve the problem, you can see these concentrated red regions. This is the point where error is high. So what we can do, we can adapt the mesh. We can rise the, for example, we can make mesh denser. We already did that near the holes because there is a perforated plate, but we can rise the approximation order. So you have a heterogeneity of the approximation order. Some elements has order 8. Some of our elements are order 2. When you rise this approximation order in the smart way, you can achieve so-called exponential convergence. So we can get the optimal solution, desired solution with desired error with the minimal computer effort. So when you do that, you have a kind of the uniform approximation error. So this is you can see that this is a logarithmic scale, so the error is more or less uniform and small. There is no concentrated zones where the error is not necessarily a good one. Andrew will tell you how you can write the error estimator and how you can do API adaptivity later on. So we have a heterogeneous. Each entity can have a different approximation order. Entity, we mean that edge, face, volume, and so on. And it's hierarchical. What hierarchical means that you can group the base functions by the order. You have a group of functions which are first order, second, third, and so on. So typically Lagrange shape functions, you cannot do that. You have to introduce the nodes, and you can see each time you increasing the approximation orders, all the shape functions are changing. So the making approximation, which is the heterogeneous, is possible, but very tedious and hard to do that. When you have a hierarchical base, you add the functions and they are grouped by the approximation order. In 2D, for example, it will look like on the figure below when we have you can see that we have some base functions associated with nodes, edges, and faces at the end. About that, you can read in the tutorial 2, Fundamentals 2, and follow that link. So, but we have, in fact, in MoFEM, we are not only restricted to the hierarchical basis, we're using Bernstein-Bressy polynomials as well for fast integration. So we're grouping the entities first by the type of the entity. So we have finite element, triangle, for example, here, and we decompose it on the sub-entities. And on each entity, we have a hierarchy of the approximations. Why are we doing that? Because then we can group the base functions by the entity, vertex, edge, face, and volume in case of 3D. So, so every finite element, in fact, can be decomposed on the sub-entities like quad, triangle, hex, or any other shape, prism, and so on. So what that mean? That means that, for example, I have this bunny, like we have seen it before. I decompose the element, and then on every element, I can run the set of the so-called user data operators, for example, to calculate the thermal problem. So what I mean that, in fact, for me, it's not longer important what is the shape of the element. It's important how many edges element has, how many nodes, and how many faces it has, and volume finally, and then I will run the so-called user data operator for each of those. How to solve this is the case for a thermal, that I have a finite element to calculate the right-hand side, finite element to calculate left-hand side, and then this heat type of the problem, you can use the heat method to calculate the geodetics on the surface of the bunny, and then see tutorial Scalar 9 if you want to see how to calculate the geodetics on the surface. So what are those? So this thing, we call it pipeline, that you set have a set of the different operators which you run on the entities. So why are we doing that? Because now when we implement the operator for a sub-entity, and what that means, that no longer shape of the element matters. You have one implementation which works for quads and triangles, or tets or hexes. It's independent of the approximation base. You can switch the approximation with the flip of the finger and use the Legendre, Jacobi, Lobato, Bernstein basis if you like. That basis which suits your needs the best. You can raise the approximation order because you're raising it by the entity. You can write the code that is independent on the dimensions. Carol will talk about that. And then at the end, you have those operators which have every complex task is split on simple operations. And then, for example, Carol can, or some group of people can implement the elasticity, another group of people can implement contact, and they put the operators in the pipeline, and suddenly you have mechanical problem with the contact. Each parts can be tested independently. And we have example like that. There are tutorials when we implement the elasticity, separately contact, and we put the things together in order to drop the bunny, elastic bunny from some height. Okay, this is what I want to tell you about that part. And if you have more questions, you can ask them over here. You can as well go to the Google Groups over that link. You can ask the questions there.